Alright, this chapter is chapter 8, Kinetic Particle Model of Matter. You can tell a lot from actually the name of this chapter, alright, what it is about. This topic is actually also covered in your chemistry and some parts of your biology. So if you're taking, you may find that some of the things are repeated, but that's good for you lah. The only thing is near the end, we'll talk a little bit in focus about this topic with regards to physics portion lah. Alright, so what does kinetic particle model and how does it relate to the states of matter? Alright, so you can have a look at this. You know that this is a picture of the SARS virus. With recent technology breaks, we are now able to actually map even the very tiniest particles that we previously couldn't see. So with advancements in technology, we can use the electron microscope to actually take pictures of the at the atomic scale. So that allows us then to have a model to describe molecules and particles and at the atomic level and how they move. Alright, so what kinetic particle model or kinetic model of matter means is, so let me just write this, kinetic particle model of matter. What it means is basically that all matters is made out of tiny little particles, and these particles are always in constant motion. So this is what kinetic particle model essentially is. It's a model of states of matter, that all states of matter are made out of these tiny little particles, and these particles are always moving. Now this model of matter is able to describe things that we see at the macro scale, at the big scale. So let me just show you with advancement in technology what we can show you. I'll just show you the video. If you are here, you can just play the video yourself. Alright, so over here you see actually a very old image of I think an electron microscope is pictures of actually atoms, the gold atoms. So if you look at it, you can see that actually the atoms are continually moving lah. So this is what the kinetic model of matter is. It is a good description of what actually happens in real life lah. So let me just play it one more time for you to see. I'll link this video here in the description of my video here. Alright, so that is proof of, rather not proof, but it is a good enough model for us to describe what is actually kinetic particle model, and that it actually really works. So what kinetic model of matter or kinetic particle model of matter actually states is that all matter is made out of these tiny little particles, and all these tiny little particles will actually move around constantly all the time. Now, so because they are moving all the time, we call that kinetic lah. As you know, kinetic has to do with motion. Now, in between these particles, there's also these forces of attraction, which in this diagram has been illustrated as a string lah. So between each of these particles, there's actually forces of attraction that keep them together. Alright, so the kinetic particle theory, if you look at it, basically what it says is that if you look at the diagram, we're talking about with reference to this diagram here. So when the structure in that figure is shaken, energy is actually transferred to what we call the kinetic store. So if you shake an object like that, then the molecules in it will move, so it gains kinetic energy. Now, when a molecule is said to gain kinetic energy, that actually affects the temperature, because the more energetic it is, the more it is vibrating, the more kinetic energy it has, then it is then able to transfer that energy to you if you are touching it, so that object will feel hot. So at the microscopic scale, we say the energy actually goes to the kinetic store of the particles. But if you're looking at it at the big scale, at the macro scale, then actually that microscopic scale that we say is the kinetic store of the particles is actually what we deem at the macro scale as the internal thermal energy of the object. Now, at the same time, you see all those little springs that were connecting the particles together, right? So these particles are actually what we call the potential store. This potential store is what we imagine, because you must remember this is a model. So this potential store is then what we imagine to be as the forces of attraction between the particles. Now, these forces of attraction then will then determine what kind of state the object is in. If the forces of attraction is strong, then the state is actually the solid state. So if I weaken this forces of attraction, or by giving it energy to the potential store, by giving it energy, I am then able to break the forces of attraction, then actually I can change the state to liquid. So when I increase the potential store, what I'm doing is I'm actually increasing, or rather weakening, the force of attraction, and that will allow me then to change state. So this is what the model actually states. Now, so just a continuation of what we discussed. As the forces of attraction between the particles get weaker, as the forces of attraction between the particles get weaker, then we say more and more the particles are able to break away and roam freely. And you know that when the particles are able to disassociate themselves, they can break away, then actually you would then have a change of state happening. Alright, so this is the important part. The kinetic particle model will actually determine what kind of observable properties that you will have from that certain state. So in a solid state, the arrangement of the particles, and you need to remember all of this, the arrangement of the particles, they are closely packed and they are arranged regularly. These particles among the three states of matter, solid, liquid, gases have the least energy. How do you describe the motion of particles in solid? They vibrate about a fixed position, and they are held together by strong attractive forces between the particles. Now, because they are closely packed and because they have regular pattern, that means my solids have the greatest density, because closely packed means my volume is the lowest. Alright, and density is equals to mass per unit volume. My volume decrease, I divide by a smaller number, my density will increase. Alright, and because they are fixed in their position, that's why my solids have a fixed volume. So this model of the matter is able to tell us, to explain to us why certain states of matter act the way they do, and because of that they also have a fixed shape. Now, I'll do the same for liquids. I'll just discuss it very quickly. You do need to memorize all of this. So in liquids, the particles are still closely packed together, but they are less closely packed as they are in solids, and they are arranged in an irregular or random pattern. The descriptor for how the particles move is that they slide over one another, and the forces are strong, but they are slightly weaker than compared to in the solids, which means then liquids have slightly lower density than solid. Because they are less closely packed together, that means the volume will be more. The same one with density equals to mass per unit volume. My volume increase a bit more, my density will then decrease. Alright, the sliding over one another means they are not fixed in place. That means they have no fixed shape. The liquid will just assume the shape of the container. But because they are still quite closely packed to one another, that's why liquids have a fixed volume. Alright, in gases, the particles are very far apart. They are arranged in an irregular pattern, and these particles in the gas, they actually have the most energy out of the three states between solid, liquid, and gases. In terms of the motion, how you describe them, they move freely in all directions, and the forces of attraction are weak. Because they are very far apart, that's why I'm not going to describe this again. The gases have the lowest densities. Alright, because of them moving, the particles being able to move freely in all directions, gases also have no fixed volume. That's why they are compressible. I can compress gas. And they also don't have any fixed shape. They will just take the shape of the container. Alright, so your job is to actually now fill up this table with the descriptors of the distance, the forces of attraction, the type of motion, the arrangement, and the energy, and what the descriptors of this model tell you about the physical property of the state. So let's start off with solids. Alright, can you all take some time, just use a pencil and fill up the table here, and then after that I'll show you the answer in a little bit. Alright, so this is the table filled up. I hope you have the same answers as I do. Alright, so distance between molecules, they are packed closely together, and because of that they are incompressible and they have high density. So each of these is tagged to a certain physical property that you can use to explain. So when they ask you why are solids, let's say, have a fixed volume, then you say there are strong forces of attraction between the particles in solid. Why does it have a fixed shape? Because the particles in solids they only vibrate about their fixed position, so that explains their fixed shape. Alright, so the next one you have to do is for liquids. So take the time to fill up the table. I'll show you the answers after this. So just pause this video now and fill up the table. Alright, so I hope you have the same answer. This is the answers for liquids. For the distance, the forces of attraction, the motion it has, the arrangement, and also the energy. Alright. Sometimes it's actually both of this. Just to bring to your attention, forces of attraction for liquids is actually also strong compared. It's about the same descriptor as solid, but actually you must make the distinction that it's slightly weaker than in solids. Alright, so I hope you have the same answer here. The last one is gas. Please do the same, and then pause the video before you check your answers. Alright, so these are the answers for gases. I hope you have the same answer. So do make a comparison between the energy levels of the three states. So gases will have the highest amount of energy. The particles will have the highest amount of energy among the three states. Right? So all of these three tables, you do have to memorize them: solids, liquid, and gases. Alright? So just to help you remember a little bit, let me just focus on this. The forces of attraction between the particles is weakest in gases. It gets stronger in liquid, and then it gets even stronger in solid. While the distance between the particles, initially in liquids they are very close together. In solids they are very close together. In liquids they are slightly further apart, but in gases they are very, very far apart. Alright, so there's a nice sim on Colorado Fat for you to go and have a look about the states of matter and how the particles actually move in the different states of matter. Alright, so I'll just show you a video of it. So these are water molecules. You see there's one oxygen and two hydrogen for each molecule. Alright, and in this state you can see they are just vibrating about their fixed position, so you can tell that this is water when it's in the solid state. Alright, so as I heat it up, so I'm going to heat it up now, you can see that actually, yep, at this point they start becoming liquid. Can you see? Alright, so they are no longer vibrating about fixed position. It becomes a bit of a random motion. So let me just put it into the liquid state, reset for you. So you can see that it assumes the shape of the container here at the bottom. Alright, and then they will vibrate and slide past one another. So this is the molecules from the kinetic model of matter perspective. This is what the molecules or the particles will look like in a liquid state. And finally, in the gaseous state, they are very far apart. They are moving all over the place. They are moving randomly. They are moving at high speeds. Alright, so this is how kinetic model of matter is able to explain the physical properties of solid and liquid and gases by assuming that the particles move in a certain way as what we have described in the tables. Alright, so this is a good app for you to play around with. You can also change the state. Instead of molecules, you can use oxygen. Oxygen exists as O2 particles, so that's why there's two molecules bonded together, or two particles bonded together. Argon exists as one atom, so you can see in liquid and gases how they will act. Alright, so play around with it. I'll link this app for you so that you can play around with it as well in the description of the video. So how do we know that actually this is what happened? Because at this point in time, no one has been able to image an atom. We don't even know whether this is what is really true. So one of the conclusive proof that actually proves that kinetic particle model actually is a quite a good enough descriptor of how particles act in reality is was given or proven by this scientist called Robert Brown. He was actually a botanist, and in 1827 what he did was because he was a botanist, so he was working a lot with pollen, all right, and these pollen grains, he noticed that when they were in water, they were doing this weird kind of jiggly move, all right. So he realized that the only way that these pollen particles can to explain why these pollen particles are moving in this jiggly fashion, he realized then that actually these pollen particles, the only thing that can allow them to move in this manner is that it is being constantly hit by invisible particles that could not be seen, which is actually the water particles, because the pollen grains were actually in water. All right, then only then he saw this jiggly kind of motion. All right, so what he surmised was that the random motion is due to the fluid particles, and these fluid particles are moving randomly in water. Remember, they are moving randomly, sliding past one another, and because they are moving randomly, they are continually hitting or bombarding the suspended pollen particles. And because I cannot see these fluid particles, I can only see the pollen particles. So these pollen particles look like they're making this kind of jiggly kind of move. So I will just show you a video. I'll show you two videos back to back. So this video will actually show you what Brownian motion looks like and a model of to help you understand a little bit better. Alright, so what this person is doing is he has lit something on fire and has got the smoke in the syringe here. He's inserting the smoke, which is actually smoke soot particles, actually can be seen. He's inserting it into this chamber, and then the smoke is now in this chamber, and then he's gonna cap it off with the microscope glass. Alright, and after that he's gonna try to see these smoke particles under a microscope. Alright, so this is what actually Robert Brown saw. But without microscope, he just used the light. So you can see all these small little sharp particles. These smoke particles actually reflect the light, and that's why you can see them, but you cannot see the water molecules, or in this case air molecules. So you can see that they're doing this weird kind of jiggly shake. So this is actually what Robert Brown noticed. So this is what we call Brownian motion. Alright, so I'll link the video in the description. So another way to show it is this. Alright, so what this guy did is he showed what actually happens with particles in Brownian motion. So these grains of sand are being continually vibrated. So these grain of sands are actually your fluid invisible particles that you cannot see, whether air or water. So these are the particles that you could see, the pollen or the smoke particles. So when he inserted it, so you imagine that you can only see this, you cannot see the rest of the particles here. You see that actually whatever you see here is whatever is happening in the Brownian motion. They're doing this weird kind of jiggly motion. So in fact, this was one of the conclusive proof that the kinetic model of matter is actually what is actually happening at the microscopic scale. So alright, so this is the video. I'm going to link the two videos in the description of the video, in the description of these two videos, so you can have a look at it. Alright, so now we've conclusive proof that kinetic model of matter, and via Brownian motion, that's proof that of kinetic model of matter. So we know that it works, and that's why we still use it to describe how particles or how matter work at the microscopic level. Which brings me to my next portion on how does the kinetic particle model relate to the temperature and pressure. So now the earlier part may not be something that is new to you. I'm sure Brownian motion is new to you. Alright, so now let's talk about how this relates to temperature and pressure. Alright, so let's go to this slide. You can have a read, pause if you need to. Alright, this brings me now to this. Now, a model, as we said, is only a representation of an idea. Alright, so it is just to help us understand. It may not be fully accurate, but it is a good enough gauge. Alright, so the kinetic particle model of matter, it can explain solid, liquid, gases, but there are other states of matter like plasma. Plasma is actually like fire. So it cannot explain things like magnetism and light. So, but it is still useful to help us understand things happening at the big scale, the microscopic scale. Right? So All right, you can have a read of this. And I'm going to talk to you about temperature. Now, in the temperature reading of a substance is an indication of the kinetic energy of the particle. So if an object is hot, the particles at the microscopic level have a lot of kinetic energy. That means it's moving very quickly. So if you're touching a pot that's very hot, all the particles in that pot are vibrating very intensely as compared to when it's at room temperature. Alright, so when you touch an object that is hot, the kinetic energy of the microscopic pot particles, when you touch it, because it is so energetic, it is able to transfer the energy to your hand or your finger when you touch it, and then your finger particles gain the energy and you feel hot, and that's why you feel the heat from this, because your particles here have now gained kinetic energy. Alright, so we need to be able to relate temperature to how the particles move. When the temperature rises, the particles are actually moving faster, or the speed of the particles are increased, which means the average kinetic energy of the particles are increasing at the microscopic scale whenever I increase the temperature of the body. Alright, notice that we say the term average here because it implies that actually it's never about just one particle. That means I cannot say that an object is 100 degrees Celsius. That means all the particles must be at certain kinetic energy or moving at a certain speed, because the particles are moving randomly and they may have slightly higher kinetic energy or slightly lower kinetic energy, but you sum up all the energy, the average gives you a good idea. So this is the important relationship I need you to remember. As the temperature increases, we say the velocity of the particle increases, and therefore the Ke, or the kinetic energy of the particle at the microscopic level, also increases. Now, so this is just the same simulation that I used just now, so you can have a look at it for the talking about state changes. Now, how does pressure, or how does kinetic model or method then explain pressure? So if I were to imagine air trapped inside a box, you know that the air particles are moving randomly and in all directions. So even though the mass of each individual particle is very small, whenever they hit the wall of the container, they're going to exert a force on the inner wall of the container. So you sum up all the energy of all these particles bouncing all over the place and hitting the walls, there will be overall a force felt on the walls. And this force is then what we call the gas pressure. So let's talk about it. When a particle hits the container wall, it will exert a force. You sum up all the forces of all the particles hitting the containers of the wall. You sum up all those, the total force exerted by the gas per unit area is then what we call the pressure of that gas. Alright? So you know this because you know pressure equals to force over area. Alright, now this is how you should explain pressure. When they ask you to explain why does gas exert pressure, because the particles are moving randomly at high speeds, it hits the container, it exerts a force. Force per unit area is pressure, that's why there's pressure. Now, which means that because I now know the relationship of temperature with particle energy, and also how the particles are able to exert pressure on the container, I am now able to do this following thing. Alright, so I'm just going to put a star here. This is just an application of what we have learned. The higher the temperature, you learn over here, the higher the temperature, the faster the particles are moving, the higher the kinetic energy. So the higher temperature, there's an increase in the velocity of the particles, which means there's an increase in the kinetic energy of the particles, which means there's an increase in the force of collision. What is this collision? The collision between the particle and the walls of the container. Because there's an increased force of the collision, therefore I have an overall increased force felt on the walls of the container. And since I know pressure is force per unit area, I have an increase in the pressure. So whenever I increase the temperature of a gas, then I will therefore increase the gas pressure that is felt on the gas. Alright, so that is actually all for this chapter that you need to know. So let me just highlight the important points for you. This one is important. The concept of how a gas, how kinetic model of matter is able to explain why there is pressure of a gas. The relationship between temperature and the velocity of a particle in kinetic model of matter. Brownian motion, you need to be able to explain why a certain particle moves is because it's being hit by the invisible air or water particles. You need to be able to describe these three tables to me. You may need to be able to describe each one of them and how that relates to the physical property that you observe in either gases, liquids, or solid. Alright, so it's a relatively short chapter. So that is it. Thank you very much. Bye bye.